مرحبتين.
اوكي. رحب فيكم اليوم ان شاء الله. This is the last topic, but I don't know, it's a circuit breaker is a big topic, sometimes very difficult to finish it in one. I'll try, but if I couldn't, I might need one more meeting. So our topic today is MV and HV circuit breaker. So I'll not look to the breakers that are at home like these ones. So these are the breakers at low voltage systems. So we have, they classify it from low MCBs. We call them the molded miniature circuit breaker. Miniature is small breakers. And these breakers normally rated up to, let's say, 100 ampere. This is for household circuit protections. And you'll find it in a distribution board that I'll show you later. And their breaking capacity, the maximum current that they break, also limited into, let's say, 5 kiloampere. And then we have another, a bigger breaker that is called molded case circuit breakers, and this is normally for the main breaker for a house, for example, okay, or larger loads. So they have larger ratings and larger breaking capacity. And for higher, like for the main breaker of, let's say, large buildings or main feeder from supply, you might see air circuit breaker looks like this, or different companies. And it's used sometimes for medium voltage, but generally it's for low voltage, still air circuit breaker, or for low voltage systems. And if you want to compare them from their breaking capacity and their current rating, for, let's say, MCBs or miniature circuit breakers, they rated up to 100 ampere, while MCCBs can go to thousands ampere, and the ACB can go to 6,000 something ampere. If you go to the breaking capacity, what's the maximum current this can break safely without being damaged, this can go up to, let's say, 10K, while the MCBs can go break fault current of 100 kiloampere, while this can go to, let's say, 150 kiloampere. So it's clearly what makes this one breaks higher current than this, and this makes it higher current than it all depends on the arc quenching mechanism. يعني قدرة البريكر انه يخمد الشرارة اللي تنتج من بعد ما البريكر يفتح السيركت، او اثناء فتح الكونتاكس of the breaker an arc is initiated, and this need to be cleared quickly or quenched quickly by the mechanism في طريقة that makes this is have higher, can break higher breaking capacity. Inshallah, the principles of those arc quenching mechanisms, inshallah, will present it today. For low voltage breakers, principles basically is very easy. Whether it is molded case circuit breaker or whether it is molded case circuit breaker or MCB, miniature circuit breaker. They both have two protective elements, which are the bimetal element, which is down here, the blue color, and this bimetal expand as current increase. So it is a a strip of two material, one expand faster than the other. And so this is dedicated for overload protection. So once it's expand, it will bend this lever, and once this lever is bent, it will switch off the circuit. And the green coil is we call it the magnetic coil. So if current passes through this coil, it generates a magnetic field. And once a magnetic field is generated, if the magnetic field is higher than threshold value as setting of the breaker, the blue plunger, this will push this also lever towards this down, and also will trip this breaker. So we have here two contacts. This is the moving contact, the blue one, and the fixed contact is here. So the one wire comes through this screw, and the second, the circuit continuity goes from this to coil, then goes to thermal elements, then from thermal elements goes to second terminal of this out. And we have a mechanism this is an arc splitter, which basically when you try to open this contacts, an arc is initiated, and especially during short circuit, the arc is larger, and to keep this arc not to explode the breaker, you need to split it to reduce its energy until it is extinguished. And as a demo, just show you here. Now, this is during, say, an overload condition where a current is small. As you can see, this is bending, and the breaker is opens. Okay. However, during short circuit, arc is initiated and this splitted somewhere here. Okay, and this is the basic principle of the breaker that we have at home, whether it is molded case circuit breakers or miniature circuit breakers. So this is very important part, which is arc quench or arc. So the curves, if you would like to see the curve tripping characteristic of this element plus this, they constitute this. So this is for the overload element, which is the bimetal element, and this is for the instantaneous. It's like a relay characteristic. We have instantaneous plus time over current, like the 51 elements, and this is the instance. So this is acting like the 50 instantaneous elements, and this is the time delayed element. This is for low voltage breakers. Also, the MCBs, they are classified according to the instantaneous elements. So type B, C, D. I don't go over these details because this is not the subject of today's for high voltage breakers. So type B, for example, are low voltage breakers, MCB breakers that operate its instantaneous elements, which is the magnetic coil. It operates at 3 to 5 times its rated current. So type B, 5 to 10 times. Type D, from 10 to 25 times its rated current. For breakers at medium voltage also can be categorized to A and B. I don't want to go to this stage, but I would like to show you for air circuit breaker looks like this. In a panel, you have the breaker. The advantage of air circuit breaker as compared to molded case circuit breaker, this is you can some of them can be racked out, can be maintainable, while the MCCBs sometimes you cannot open them. once it get damaged, that's it, you have to replace them. While this one, you can maintain its contacts. So this is the this is an illustrations of this is now all talking about now the low voltage breakers. Okay, so this is air circuit breakers, which looks like this, and so this part is changeable. I can change the unit. This is the trip unit now. This looks like the brain, the relay, which replaced the relay. Okay, so in this here you have the settings for the protection, settings for the overcurrent, settings, whether it is like now we have different now. This is now electronics in MCCBs and MCBs. The mechanism, the protection elements is electromechanical, while here it's electronic, where you sense the currents and voltages or electronically, and you compare it with the setting. So setting I can set, let's say the overcurrent elements, or for the ground elements, I can change the time delay, the pickup settings from these ones. Sorry. And I have also here I can start and stop buttons, and you have a lever here where I can charge a spring, the spring that you want to open, or you want to switch a breaker or open a breaker. Okay, so you need to charge it. Okay, so the speed at which the breaker opens relies on a spring. Okay, you compress a spring so that when there is a fault or you want to open a breaker, the spring helps the breaker contacts to open very fast. If you look to the so these are the low voltage breakers. I don't want to spend much on it. My interest today to illustrate to you. So this is the panel in which you will find these breakers. And the specification, these are the panels. So this is the specifications on voltage rating, the breaking capacity. They specify maximum. This is the breaking capacity ICU, which is 25 kiloampere. This maximum current. The rated voltage that you can use this up to 660 volt. What's the category? I told you category A and B. Category normally B can be used for coordination because you have a time setting, but category A is not designed for doesn't have short time delay. In MCBs and DBs, you can see them inside a distribution board. So the arrangement in a house, for example, supply comes to fuses, then to a meter, then to a main breaker, which is in our house as MCCBs. This feeds then the a panel, a distribution board, we call it, in which we have different type of protective devices. And these are the miniature circuit breaker is somewhere here. Like these ones are the miniature circuit breakers. But in addition, we have a device. So miniature circuit breaker provide overcurrent protections. But for shock protection, we have another device. It's called the residual current device, RCD. which acts like a differential protection device, which compare between the currents in the line and neutral. If there's a difference, it trips, okay, circuits. So if you learn from this high voltage equipments, you will be able to understand this low voltage equipments easily. And this is distribution boards where we have this is three-phase distribution boards, and these are the small breakers, and these two are the RCDs, or residual current devices. Okay, residual current devices, they protect, they can detect very small current that goes to earth, and therefore to provide electrical shock protection. Their principles is very simple. It's here. The current passes in the line and neutral are same. So the magnetic field generated by the current in the line and neutral, they will cancel each other. So the net flux in the core becomes zero, and there will be no induced EMF in this coil that will trip the breaker. However, when you have a short circuit, like line to neutral, also there will be no net flux and there will be no actions. So RCD, residual current devices, does not operate during short circuit or overload or during normal operating conditions. Only operates when you have a leakage, a fault that goes through human tube or goes through the body of the device to ground. So when you have a leakage of currents, then the line current, part of it goes to ground, for example, or part of it goes to the neutral. So when there is a difference of, let's say, at least 30 milliampere for 30 ampere sensitive devices, this device will trip. So the neutral current flux will be different than the neutral current flux because the current are different. As a result, the net flux will be not zero. That will induce a voltage here that will trip the coil. This is the principles, like a differential, but this is not a differential. So all of this is related to low voltage. They looks like this is for a three-phase, and they looks like this, and they have sensitivity. Their written is like I delta N 30 milliampere, which means if there is a difference in current between line neutral, or if it's a single phase, of 30 milliampere will trip instantaneously. But there are different sensitivities. We have 30, 300 milliampere, and so forth. And these protection devices are dedicated to detect ground faults to provide protection against electrical shock protection, so protect humans, while MCCBs and MCBs are protecting the devices, the conductors, okay, from overcurrent. So these are at low voltage systems, which I don't want to, and this is not what I want to explain, Shabab. Do you have any questions before I go to the موضوع اليوم? Okay, so in high voltage breaker, from the picture, they looks nice. It's not like what you see. So this is a breaker, okay, and so breaker is being used a lot. So we can have we have different types of switching devices. So in this, I'll focus on the circuit breakers. So I'll start with some definitions, how they classify circuit breaker for high voltage systems, how they historically developed. Then I'll go to the switching in power systems, how the current and voltage looks like when a breaker open circuits. Then we'll come to this is what is important: the arc quenching theory. How the circuit breaker get rid of the arc. Then we'll go for parts of what are the main parts of a circuit breaker for high voltage and medium applications. I'll then go to their working principles of some of the breakers, like air magnetic circuit breakers. But I will not cover some of the breaker that is obsolete now, like oil circuit breaker is obsolete. خلاص, it's not used anymore, so I don't want to cover it. But we'll cover like breaker like vacuum and SF6. And then we'll go, what are the electrical specifications that electrical engineer need to know about the circuit breakers. Now, how do you choose a circuit breaker for that will be able to break a short circuit current? So I'll show you some examples if possible, and we'll define what is a switchgear, inshallah. What is the difference between a distribution board, a switchboard, a switchgear, okay, and so forth. If you look to these pictures, do you know what is the difference between a switchgear, a circuit breaker, a load switch, and a disconnector, Shabab?
Switchgear can be switched manually, but the circuit breaker can depend on the fault and relay command, right? Or what?
The switchgear can be switched independently?
No, manually, but the circuit breaker dependently.
Maybe what you mean a switch. The switch in general, a load switch is, it can be motorized. Generally, it's a manual, okay, operated, but can be motorized switch. But what makes a switch is different. The switch is its capability to, and we compare these elements and their capability to close or open. It's their ability to open or close a current. So what's the maximum current that these devices can switch on or break? Okay. So in switches, generally, they are designed to, you can operate them, switch a load current is fine, up to full load current, or either you close or open, okay? But they are not designed to break short circuits, okay? So this is one important thing. Circuit breakers, which is like this one, is it's capable of breaking short circuits. They are designed to break high currents. So it can make or close into faults. It can close a load current. It can also open when there is a short circuits. Okay. While a disconnector, it is not designed at all even to break fault current. It is not designed to even sometimes break load currents. So it's not intended for switching. It is intended for purpose of isolation a device. You want to isolate it. So they provide large gaps, distance between the contacts, so that the two sides of the isolator, the two components at the two sides of the disconnector are physically isolated. So this could be either motorized or it could be also manual. But they are not used even to switch a load. So we need, normally we switch a breaker first, then we disconnect the circuit through the disconnector. However, a switchgear could be a combination of a circuit breaker, of a disconnector. It could have an earth switch. It has okay, metering devices, it could have protection devices. So it's purpose to a switchgear which is like this. Sorry. So there are different type of switchgears, but it is an integration or a combination of different devices integrated together for the purpose of control, protection, and isolation. Okay. At the same time. So it has a protection devices, control panel, it has CTs, VTs, it has a breaker in it, it has disconnectors in it. So I'll come to this inshallah later. This is a photo of a circuit breaker of medium or high voltage circuit breakers. I'll come what are they, how they are classified. So these are breakers, but this is a switch gear. But switchgear for medium voltage systems and is different than this. Breakers can be used so many. I can use it at the generation for a generator, circuit breaker to disconnect the generator from the systems. I can use them at the transmission systems. I can use them at distribution systems. Okay, so there are so many breakers. I showed you the low voltage breakers, but today, inshallah, I'll focus on the breakers at the medium voltage. To show you a single line diagram from one of the power plant. This is a real single line diagram from a plant. We have now the single line showing two generators connected to a two bus here, okay, a double bus, and these are the transmission line. This breaker that connect to a transmission line. So each generators here, I don't know if you can see it clearly. This is the generator, which is connected to a star delta transformer. Sorry, a delta star transformer, delta at the generator side, star at the HV side. And it's grounded here. So grounding, star is grounded to limit the fault current, and then we have a breaker that connects either to this bus or this bus. Okay, and between these two, you see this a small line. This is the isolators, okay, or disconnectors. And this is a breaker, and this you have a small also disconnector disconnected to earth. So I can also connect. Suppose I am want to take the breaker out of service, you can switch this off, okay, and you open these two isolators and you ground its terminals. You connect them to ground through also this disconnectors, small disconnectors. This is now the output of the generator can be also connected to another transformer, like 3-winding transformer or 2-winding transformer, to step it down to a lower voltage. So this is like from 15 kV, for example, it can go to, let's say, 220 kV. This is the 220 kV circuit. So also at the this is the feeder or transmission line. It has a breaker. It has also an earth switch. This is an earth switch where you connect during service maintenance. You disconnect the breaker. You connect now. You ground this circuit so that during maintenance is safe, okay, to operate in this. So where is the in the breaker here for a generator, there is one breaker here which is not clearly shown here. So this is a generator circuit breaker shown here. These breakers also breakers. We have also a breakers. This voltage here, this transformer step down to 11 kV. So we have also breaker which is shown as VCB. I don't know if you can see this. This is VCB, vacuum circuit breakers. but at the voltage here, at the 220 kV, I have GIS, or gas insulated switchgear. So what's a switchgear? Is the combination of all of this. It's a buses, breakers, CTs, VTs for measurements and protection, earth switches, okay, disconnectors. So all of this is called a switchgear. Okay. So our today is not to focus on the switchgear, we focus on the breaker types only. So so this is 220 kV gas insulated switchgear, and see why there are different types of switchgear based on the insulation medium. We have here, because this bus bar, which is split it into two sections, so this is a bus tie. So this is at 11 kV, so, and also in this it has many breakers leaving this bus bars. So these breakers are vacuum, so we call this vacuum circuit breaker for 11 kV switchgear. We have breakers of vacuum circuit breakers here. At the maybe at the low voltage level, this 11 kV also stepped down by transformers. So we have two 400 volt line-to-line voltage, and then it's feed the same motors, lighting, all the services, and because this is a low voltage, 400 voltage, we call this 400 voltage switchgear, or sometimes we call it as a switchboard. So, and here we use, let's say, ACB breakers at low voltage, but here is vacuum circuit breaker, here gas insulated switchgears or breakers, or SF6. This is, so inshallah today I will focus on the breakers only. It's not on the switchgears, shabab. Okay. So what's the definition of a breaker? Circuit breakers. It depends. If you look at from the LV system, it's different from the high voltage systems. According to the ANSI, which is the American National Standard Institute, they put this definition. It's a mechanical switch, a breaker. Mechanical switching device. What is able to make means it can close into, make, carry continuously, and break a current under normal operating conditions, which is load conditions, no fault conditions. When I say make, means I can close. Carry means it is when it is on a closed position, it can carry this current continuously. And break means when you open it. So it can make, carry, and break a normal current, but it's also capable of making, carrying, and breaking a short circuit current. So carrying for a specified time. At the end, when there is a short circuit, the breaker is not designed to carry that short circuit current for indefinite time. There is always breakers specified. It's breaking capacity for a duration of time. So there is a 1 second rating or 3 second ratings that the breaker can handle while it is in a closed position during short circuits. Okay, Shabab? So this is a breaker. This is the definition of a breaker. So it's not related. There is nothing here mentioned about the protection. It's a mechanical device. So in the high voltage system, this breaker needs a command from a relay or a protective device to open it. Okay. While in low voltage system, the definitions, it's a device designed to open and close a circuit with non-automatic means, like manual, or open the circuit automatically. Why it's open the circuit automatically? Because it has a protection device integrated with it. On a predetermined, which is the settings, predetermined overcurrent without damage. to itself when properly applied within its rating. And when you choose a low voltage breaker rating and its breaking capacity properly, it can disconnect short circuit, okay, uh, without damaging itself. يعني فبعض الطلاب مثلا ممكن يجيب لي هاي definition to يعني لاحظت من بعض presentation they bring the definition of this for defining all breaker. No, this is only applicable to a low voltage breakers, okay, where it can automatically trip on a predefined because it's the protection system integrated with the as I showed you in the beginning of the this presentation. There is a basic requirements for a breaker or skivvet, like it should be when it is in a closed position should have a like it acts as a zero resistance. When it is in open position, it should be like an insulator, or it should switch on very quickly, okay, open in very short time, and close also in very short time. It must be reliable and it should withstand and shouldn't cause an over voltage during switching. The classifications of circuit breaker, they can be classified based on their voltage level into low voltage. Any voltage less than 1000 is considered as a low voltage. For the breaker at home is a low voltage breakers. Okay. Medium voltage starting from 1000 volt, which is 1 kV, up to 50, let's say 2 kV. So the breakers at the 11 kV is still in, like in Bahrain, we still high voltage consumer can still use 11 kV supply, so it is considered as medium voltage breakers. If the voltage of the circuit is 11 kV. At higher voltage, high voltage breakers are from 66, for example, to 700 and about 750 kV. Ultra high voltage above this voltage. Okay. So this is one classification. Classification based on their location. Sometimes they call it indoor breakers and there's outdoor breakers. We have based on their external physical structure design, we have a live tank and a dead tank. Live tank where the interrupter, the contacts location is not grounded, where the chamber on which is hold the show you later inshallah, dead tank where the chamber on which the contacts are located is grounded, it's connected ground. We have also the breaker are classified also based on the insulation and medium. Insulation and interrupting medium. As air circuit breaker, so air is now the insulation medium. We call it air circuit breaker. The oil, we call it oil circuit breaker. Vacuum, we call it vacuum circuit breaker. And gas, we can use SF6 or G-cube. This is one of the latest gases, or a mix of gases. They call it gas circuit breaker. So historically, the like from 1900, this shows you the historic development time in years versus its breaking capacity, its interrupting capacity. The maximum current that this breakers can handle. Initially, the breakers are designed not to based on oil as an insulation media in roughly hundreds, 1930 something. Then their breaking capacity is low. So then they have air blast air blast with multi-break points. So air blast, they have braking capacity like in this one's for oil almost breaker being extinct on 1960s. It's not used. So there's no point to explain it to you today, okay, if it's not used anymore. And air blast breakers, then they used, but they have where air is used as the insulation media. They can have braking capacity is limited. Still, we have a limited braking capacity. In 1970s, they have now a vacuum, which is widely now commonly used for a medium voltage, like up to 140 volt. And this is considered a high voltage, but for medium voltage, the majority of vacuum is used on a medium voltage range, but still used widely now nowadays. So majority of, we'll say 90 or 80%, I would say 80% of the breakers at the medium voltage levels are vacuum circuit breakers, but they have their limited braking capacities. For SF6, which is gas circuit breakers, they have higher braking capacity. That's why they can be used at high voltage systems. So they have high braking capacity and they can be used for high voltage systems and extra high voltage systems. So most of the breaker now at the high voltage systems are SF6. So how do we, how the breaker switch current? So you can switch a breaker when there is already a fault. Before you switch a breaker, you have a short circuit already, so you switch on to fault, or you have a fault while the breaker is closed, a fault occurs, then the breaker should open that fault. Okay, so you have these two scenarios. So when a fault occurs, the current has a decaying DC with it, as I explained before. So current goes to peak, and this called then decays, depends on the time constant of the decaying DC, until it reaches steady state. Okay. In our short circuit calculation, normally what you will do will get the steady state current. So when we rate a circuit breaker, when you choose a circuit breaker, at what current we should choose it? We should choose it to break this current, Shabab, or this current, or this current, or which current you expect? Shabab?
None of all of them, because it's normal condition, right?
هذا normal current الحين during short circuit يعني current. لا الحين في فرق. أنا لما أقول current rating or circuit breaker, it is chosen based on the full load current. Okay. نتكلم عن its breaking capacity, يعني قدرة البريكر إنه يفصل short circuit current without being damaged. فعندنا different ratings. يعني one of the ratings اللي هي النقطة هاي لازم يكون قادر إنه close into faults. Okay, يعني while you are closing a breaker can't موجود fault already, so it should handle this high current. We call it the peak current duty, or we call it close and latch duty of the breaker. So breaker manufacturer will give you this. What is it? But this is in peak, kiloampere peak. So it's the maximum peak current after half a cycle that the circuit breaker can handle. Okay. So each breaker has its maximum peak current that can handle. The second specification by manufacturer of circuit breaker is called the interrupting duty, or the current that the circuit breaker can break off at the contact opening time. يعني a fault happens, then a relay takes time until and give let's say a breaker command. A breaker is a mechanical device, will take time until it's open. So this is the, let's say, the time at which the breaker contacts start to open. And we should use this one for rating. This is the current that includes both AC and DC component. This is the DC components on top of AC component. So it should be able to break this current, okay? And this is where they specify the breaking capacity of the breakers. And also in the breaker, they specify the short time duty, which means how long this breaker should wait closed while it is in a closed status during short circuit for the purpose of coordination. يعني طالما في faults the breakers doesn't operate. You want the other primary breakers to operate, so it should have waits. How long this should wait when there is a short circuit at this specified current? They said, okay, some breaker, they call this specification a short time duty, or and it is normally specified for 1 second or 3 seconds or 2 seconds. They are mentioned by the breaker. So this is the maximum time on which the short circuit fault current passes through the breaker while it is closing, and this thermal heat generated by this short circuit can be handled by this breaker without being damaged. Okay. So these are related to short circuit current. There are also something related to the voltage. Okay, once suppose a fault is this is the system voltage, the dotted, and the currents is here. So suppose now the breaker is tripped, so it's opened. You initiate a current. So this is the fault current before a breaker opens. So the breaker command is given here where you want it to open. So these small ones represent the voltage at the contacts while it is opening. While it's trying to open, it is physically open, but still you have arc, and the arc will have create a voltage drop across the contacts. When the arc is extinguished, arc is removed, then the voltage will shoot up and down until it's settled down. This voltage is called the transient recovery voltage. And this voltage depends on the circuit. This is capacitive circuit that you are trying to open, or it is active, is XR ratio. There are so many parameters that decide the shape of this voltage. So I have to look to this maximum voltage. So is the breaker is able to withstand that transient voltage? So this is called the dielectric recovery capability of the breaker. If the insulation medium, which is oil or gas or it has also dielectric strength. So if the dielectric strength of the if the insulation is lower than this, then the breaker will fail to open, and you'll have something called restriking. The current will still continue because of an arcing. I'll come to this later, inshallah. So this is another aspect that we should look to is the transient recovery voltage. Especially we are talking about generator breakers and high voltage breakers. Now, how do you get rid of the spark? There are three theories. Before I get to theory, I'll show you the here. What do you mean by the problem? This link is not working with my. I have to change the browser. Now you see the arc is in air. This is the since arc is they are opening now. This is the breaker, a switch. So now quench that arc is this is what makes it different. I can use.
Doctor, we didn't hear you. What are you trying to say about the arc? We didn't hear you about what are you trying to say about the arc?
But did you see the arc?
Yes.
Okay. فكل أقول لكم إن this is like open air substations, and the one that opens here is like a switch, okay, or a disconnector. But as you can, it was a load condition. It's not. This was not during a short circuit. But see the arc, the plasma, the arc. It can extend until it's extinguished. يعني بالتالي when you open a breaker من لحظة opening physically doesn't mean electrically is disconnected لأن the current will flow through the arc. So until all the arc is extinguished, then we say there is a current is broken or a fault is cleared. Okay. So how do we get rid of this arc? We have different principles. I tried to skip some of the slides because it's too long. So the arc quenching theories, we have roughly many theories. How do you get rid of this arc? We can use the high resistance or interruption principles. So, like we increase the arc resistance so that the current decreases and becomes zero. And so this can be done by cooling the arc. يعني you cool the arc to to extinguish it, or increase the arc length. يعني you increase the arc length so that it reduce also and it can be extinguished by increasing the arc length, or by splitting the arc into sections. And this is where it is applied in air circuit breakers. So the arc splitter I showed you in low voltage system, it is the principles here. So you split the arc into sections to make it weaker, and then you extinguish it. And there is another theory of getting for extinguishing arcs. Space is on the energy balance. So if the energy loss from the arc, when arc is cooled, due to the cooling medium, or as against heat generated from the fault current. So if the heat generated fault current is less than the cooling, then they will be able to extinguish this arc. So this is called the arc quenching theory, or so which is based on heat energy balance. The third principle is based on dielectric race theory, they call it. And when the current just cross zero, at the zero crossing of the current, there is when you try to open the contacts, so there will be a race between the dielectric of the medium, of the insulation medium, like air or gas or oil, and the voltage that will develop, which is transient recovery voltage. If the transient recovery voltage across the contact is higher than the insulation the dielectric of the insulation, then the spark will not be extinguished. So the theory here says you have to increase the dielectric strength faster, higher than the voltage that will develop on the contacts, so that you can get rid of the spark. So I'll show you now here these theories. So I have, let's say, this is the fixed contacts of the breaker, and this is a moving contacts. Suppose now they were closed. And you open, you push this one to open. So the arc can be forced by air, sometimes forced by magnetic force towards the splitter, the arc splitter or arc shoots. هاي نفس الارك سبليت اللي شفت راويتكم اياه في الفولتج بريكر. So the arc will split into here. The magnetic force will make it towards, or the air, blow air here, for example. Sometimes I will move this arc so that it has longer length, and also I'll split it. So these are like insulation. So they act both. Sometimes they act for cooling and splitting. Okay, the arc. And so you elongate the arc length, so the arc will be weaker, and at the same time you split it, so the arc will be weaker, and as a result it's extinguished. So this is the principles based on the first theory, which is used on air circuit breakers. And the second theory based on the energy. Okay, so like in SF6, the gas has very good dielectric properties, but also it's used to cool the arc. So on the left-hand side, this one shows you the fixed contacts, and these are the moving contacts we have. This is the moving contact. So initially, this was inside here. Okay, so they are a continuity of current through these two terminals. When you open this moving contact, you move it away from here, the arc is initiated, and the SF6 gas is pressurized, so it passes through this nozzle, it goes here, and also it goes inside here. So what it does, it will cool this heat. There will be a heat generated from the arc, نتيجة I square, and also there is cooling from the gas. And when the cooling energy is more than the heating energy, then this arc will be extinguished. This is the principles of the second principle of energy balance theory, which is used in. But also these breakers has to be also very fast when you open, so that so this is the principles of this is the arc. When you open it, there is ohmic heating from the current, and there is a cooling energy from cooling too from the gas and from the ambient temperatures. So this is the theory. For the dielectric, the third theory is used in for vacuum circuit breakers. And vacuum circuit breakers, so this is the let's say the voltage. It's like a voltage race. Which one faster than the other? Now I'm drawing here the voltages A, B, C, three curves. A, B, this. So so A is so this is the curve A, B, and C. This is the voltage that will develop across the contact. Okay, while you are trying to open the contacts, a voltage will develop across the contact. This is the transient recovery voltage. Three scenarios. And the one here, let me check if I have a pointer. And this one, the top one, this one is the dielectric recovery of the insulation medium of SF6 or gas or air or oil. How it retain its dielectric properties. Okay, so for the first case, so in this case, for case A, this one, the dielectric property recovery of the insulation media is always larger than the voltage that will develop across the contacts after opening. So that's why you have a successful interruptions of current. However, like in case B, initially the voltage that will develop is lower than the insulation media recovery, so it is it will quench the current, but at this point the voltage across contacts is higher than the insulation dielectric strength. So as a result, it will break again. The arc will reignite again, and the current will not stop. And the third here, initially there is no, the breaker looks like it is the dielectric strength voltage is more, but at this point the voltage becomes across contacts higher than dielectric strength, so there will be an arc reignite again. So for this theory, the dielectric should retain its recovery very quickly and faster than the transient recovery voltage for the successful clearing of the arc. So this is like a voltage across contacts, and this is the dielectric build up across from the medium of the oil, for example. So this is now will be a successful tripping or clearing of faults, while here at this point it will there will be a failure. It will the breaker will not extinguish the arc after this point. This is just an illustrations of breaker being initiated to close operation this point. This is the voltage and this is the current. When you close it, there will be a current flow. And at this point, a trip signal is given to a breaker, but the breaker needs a time to open. So at this point, the breaker contacts started to separate at this point. But the current still flowing. Why? Because of the arc. Now, at this point, the arc is the recovery voltage of the medium of the dielectric is lower than the voltage, so the arc is reignited and the current still flowing until this point where the recovery voltage less than the dielectric, then the current is stopped, and the voltage again. This is the voltage across contacts. When it's closed, the voltage across contact is 0, right? The current is flowing through the contacts. So this is the sometimes the breaker take longer time to break the currents because of this reignition of the arcing. I'll come to this, inshallah. There are, when I say dielectric strength of the medium, I mean the insulation used. Is it air or SF6, oil or vacuum? All of them, they have different dielectric performance. Okay, if you compare air, this is the dielectric voltage of the medium with respect to the distance between the contacts. For air, I can use it to a limited voltage, let's say, because the air can be broken at a voltage higher than, let's say, in this view, about 30 millimeter, 3 cm gap between the contacts of an air. So the air will be broken, will be ionized at a level of, let's say, 50, 70 kilovolt, and it will be broken. While SF6 can, for the same distance between the contacts, it can handle up to, let's say, 170 kilovolt. Oil this is when the pressure of the SF6 is 1 bar. But if you use 5 bar, it can withstand even larger voltages. That's why the SF6 gas are pressurized so that they can handle high voltage. Their dielectric properties is getting better. In vacuum, they have very good properties at short distances. As you can see, even with 2 to 4 milli between gap, they have better properties dielectric than SF6. So like here, up to, let's say, 2-3 milli, I have 100 kV dielectric properties. So I can use this for medium voltage applications with a small gap. A small gap will help to reduce the size of the breaker. And why the vacuum as at very low? Vacuum at very low, because their dielectric property becomes constant as very low vacuum at a pressure of 10 to the power minus 9 bars. And it is kept at that low level so that even when it's leaking, because vacuum tubes are like this one, the tube is sealed. And these are the contacts, the sealed and this under vacuum. So it's sealed for lifetime. So what they do, they try to make the vacuum at low enough so that even when this, because of operation, the vacuum reduces, it doesn't lose its property. Okay. So what are the breaker bars? These are the breaker bars, mainly 3 parts. The the interrupting or the arcing chamber, which is, let's say this is a high voltage 60 kV live breaker. This is the portion which is the interrupting, or they call it the arc chamber, in which the main contacts are located. Okay, the moving and fixed contacts are here. And these contacts are here insulated either with air or gas or oil. And we have operating mechanism. The mechanism that closes and opens the breaker, okay? And they have different mechanisms. We can use a spring to close and open the breaker. We can use hydraulic, okay, to open and close the breaker. You have magnetic. You have so many operating mechanisms. And we have some supporting insulation. Okay, so this is the operating mechanism. We have the breaker chamber, in which and these are the insulation. This is one part, this one phase, second phase, the third phase. These normally here is the CTs of the breakers. For low voltage breakers, this is a medium voltage breakers. You can see here this is the operating mechanism. We have spring. The spring 1, spring 2, 1 for closing, 1 for opening. Okay, and so this is the mechanical springs we have, and on the other side we have this is the front view in the panel, and this is the side view. This is the interrupter or the breaker interrupter, which is a vacuum now, a vacuum tube. I'll come to this, what's inside vacuum tubes. This is insulator. So the breaker is connected terminals is this. So this goes to the one terminal of the breaker, and current flows this side, outside. So this is the terminals. For medium voltage, so high voltage breakers, this is the interrupting chamber. Okay, these are CTs, and this is the insulation medium. Inside here could be a gas inside gas. Mechanical, this operating mechanism could be a spring, as I showed you, right? So these are the circuit breaker contacts, and it is open or closed based on these two springs. Okay, one is for closing, one for opening. We have different mechanism, or oil or hydraulic based. We use pistons to close a breaker and open a breaker, pressurized oil. For air circuit breakers, normally the air is the insulation medium, and the current passes through from one terminal. Suppose this is the fixed terminal, and this is the moving terminals. These, so the current passes from here to here, but when also through here. When you try to open the breaker, some breakers, they have something called arcing contacts. The main contacts plus arcing contacts. Arcing contacts are designed to handle the arc. So the current will flow through the arcing contacts. Yeah, normally the main contacts operate first, then the arcing contacts operate. Open, sorry. So the arc will be splitted through the arc splitter until it's extinguished. For air blast, you blow air. So where are the contacts? This is a fixed contact, and this is the moving contact out. The current flow this way. When you try to open these two contacts, there will be a pressurized air blown through the contacts opening. So it will elongate the arc and split it through arc splitter. So that's what this way I can, this is called air blast. You blow air through the contacts opening so that the arc is extinguished. We have vacuum. So what does this require? A pressurized air. It is very noisy. It is this is also being out of phasing out nowadays, which is nowadays mostly uses vacuum for high voltage, for medium voltage applications, and SF6, which is for high voltage applications. So in vacuum, vacuum normally it has very superior dielectric properties. The vacuum is like a tube where I'll show you now a figure. I don't know here. This is a vacuum tube. Okay, this is the contacts. One is fixed, one is moving. This is the lower one is moving, and it's made of an alloy. These contacts made of an alloy like copper plus, let's say, chromium. This is the bellows. It's like a spring where it helps to close and open the moving contacts, and it is fully sealed. So this here, it will be under vacuum. So the arc will be under vacuum. So this will be sealed for lifetime. So normally it will takes years. Normally their life, they stays in service for 20 to 30 years. This technology is very mature. It's been in market for more than 50 years and has very high reliability, and represent almost 80% of the market are in low voltage or medium voltage markets. Most of the breakers are vacuum circuit breakers nowadays. And they can be used up to, let's say, 245 kV. But they have a disadvantage. They cannot be repaired because you cannot open them. Okay, if you lose the vacuum or there is a internal failure, you cannot open it. So you lose it. That's it. It's not economical for low voltage system. That's why we don't use it for low voltage breakers as compared to air breaker. Air breaker is dominantly used on low voltage systems. And it has technical difficulties for higher voltage. That's why it is very commonly used on medium voltage applications. The problem of this vacuum, when you deal with the decaying DC, it requires that the current pass through zero. So when you have a generator breakers where the current does not cross zero, okay, initially, this will create a delay in opening a breaker, because you don't have zero crossing, as I will show you, inshallah, on a different slides. So it could be as like a medium voltage breaker where here the vacuum tubes here, or it could be a high voltage breaker where the vacuum tube somewhere here, like here in this is the vacuum tube. As SF6, I would like to close with this one. SF6 breakers also is a mature now technology. It's been predominantly used in high voltage and extra high voltage applications. So all the breakers at high voltage, they are SF6. The SF6 is a gas. Okay, it's the gas. It has very superior dielectric properties, insulation properties. it is 2 to 3 times better than air. It has high braking capacities. It has better heat transfer, and it is non-flammable, non-poisonous, and odorless. Doesn't have smell. However, it can be also opened. And you can open a SF6 breaker for maintenance, but you cannot open, let's say, vacuum. Vacuum, you cannot open the vacuum tube. What is disadvantage is the concern of SF6 with regards to greenhouses. SF6 is one of the greenhouses gases, and it will be it causes a global warming, and that's why that's why now there is an advancement in looking for replacement for SF6. There are a mixture of gases. There are other types of gases that are now trying to be tested and to replace SF6. The quenching principle is same as I mentioned before. This I already explained. This is now in a closed position. The current flows. This is the fixed contacts, and the green ones are the moving contacts. And now the current flows from here through this, goes to the other side of the breaker. So the yellow here is the SF6 gas. It is trapped in this chamber, in the cylinder here. When you try to open it, okay, this pressure will squeeze, will increases by this piston, and it will go. Now there is no point, there is no place for it to leak because of this close here. So once the contacts, the fixed contacts separate from the contacts, the moving contacts, now the gas will flow first of all through this, okay, and then once this is also reached to beyond the nozzle, the gas will go through here. So that's why we will be able to quench the arc. This is internal constructions of the SF6. This is the mechanism to open and close the breaker, and this is the SF6 chamber, interrupter, we call it. To increase sometimes the braking capacity for higher voltage, we use sometimes more than one breaker in series. This is one breaker, this series with another breaker, so that they can be used for higher voltages. Okay, and this is a live tank where the contacts at the same potential as the voltage. Okay, the chamber here is at the same potential as the line voltage, while in a dead tank, the chamber here, the chamber in which the contacts are located are at ground potential. It's not the contacts is grounded. It means this container in which there is a contact is grounded. So that's why they call it a dead tank. So like here, this is a single breaker. This is a double breaker. So this is like in series. This is one breaker, this second one in series, so that can use for higher voltages. I'll stop here. This is what's the next part, where the specification, the electrical specifications, that is also very important for you to know. I'll try to cover it in addition to providing examples. How do you choose a breakers? Okay. I'll stop here, inshallah. In the next lecture, I'll try to present what are the electrical specifications of circuit breakers, and how do we choose them with some examples. Do you have any questions, Shabab? This is very long. I skipped many slides for the sake of finishing, but it's very long. So I need one more lecture, inshallah, on next week. Monday, I'll try to finish this, inshallah. With examples, things will get clearer. How do you select a breaker and so forth? See, as you can see, it is very complex as compared to low voltage breakers. في أي سؤال شباب؟ موسى.
دكتور عفوا كنت بسألك هل في اوفيس اور تكون بالجامعة لو كان لنا أسئلة بخصوص الفاينل يعني؟
الحين لأنه بسبب صار عندنا الحين تواريخ نقدر نتواجد فيها، يعني بسبب لأن احنا الحين صاير أصفر، فصار إن كل مجموعة لازم يكون يقل الكادر في الجامعة إلى 30%. فإحنا موزعيننا الأسبوع أنا ما أقدر أروح الجامعة، الأسبوع القادم ممكن. زين. بس إذا في أي شيء يعني بدل ما يكون أوفيس أور في المكتب ممكن فيرتشوال أوفيس أورز، يعني يكون وياك. يعني إيش المانع إن نجتمع ثرو تيمز؟
يصير بعد دكتور، بس يعني كنت أسأل إذا في كم مجال يعني.
إذا كنت يعني الأسبوع الجاي يعني ممكن إذا في هذا نرتب، إذا أنت في حاجة ضرورية أن تكون فيس تو فيس.
ما في مشكلة. الله يعطيك العافية دكتور.
خير إن شاء الله موسى. مع السلامة.
السلام عليكم.